Hi, I'm Josh, the CEO and co-founder of Emerge Tools. Today, I'm excited to walk you through a quick example of how to debug a performance regression using Emerge's flame graph diffs. For this example, we'll be comparing the startup time of two different builds of Wikipedia's open source app. Emerge does have full native cross-platform support for iOS and Android, but for the purposes of this demo, we'll be looking at Wikipedia's iOS app. In this performance comparison, the first build is generated from a commit on the main branch, while the second is from a pull request with a theoretical new feature built off of that commit. Let's see if we can identify any regressions or improvements that may have occurred in the pull request. Once fully integrated, Emerge generates a flame graph diff similar to this one on every pull request. Each box shown here gives us a graphical representation of how long the app spent within each method call. Using our innovative physical device testing infrastructure, we're able to collect many stack traces of what the app was doing during startup. We then organize these stacks into the tree structure you see here. The length of each of these boxes is proportional to the amount of time that method took relative to the whole startup. For example, if we go down a couple rows from the top, we see a familiar function. Application did finish launching with options. Now, this box is, let's say, 30% of the width of the screen, meaning that the app spent about 30% of its startup time in this method. Now you may be wondering why some of the method names are in red boxes, while some are in gray boxes. This is because each box is colored by how much more or less time we spent in that method with our new build generated from the pull request versus the build on the main branch. If the method took more time in the new build of the app, it gets colored red, indicating a regression. But if it took less time, it gets colored green, indicating an improvement, which we don't see here. The bigger the difference is, as a percentage of the total time, the stronger the color is. If we look at application did finish launching with options, we can see it's a dark red, meaning there's a significant regression here that's impacted the overall startup time. Mousing over it, we can see that it took about 59 milliseconds, and as a whole, our new build of the app from this pull request caused about a 15% increase in startup time. This increase might be because this method itself is doing more work, maybe from performing some large calculation, or it might be because one of the methods that it calls is doing more work. If we look one level down at the methods it's called into, we see three main ones: load models, app view controller init, and launch app in window. One of these, load models, is red, and roughly the same shade of red as application did finish launching. So it's clear that application did finish launching's increase was caused by the increase in this method that it called. This pattern is pretty typical for flame graphs. We get a sort of trail of breadcrumbs, a downward trail of red methods until we find the one that was actually doing the work. If we follow this trail down, we can see that our load models call into a JSON parsing method, and the trail ends there. It appears that this JSON serialization we added in this PR is causing an approximate 15% increase to startup time. With that in mind, we might decide to do this JSON parsing on a background thread, or reduce the amount of JSON being parsed, or some other optimization technique to mitigate this regression. Now, the real fun begins, as I get to showcase some of our more advanced features. First, let's look at collapse system calls. We enable this feature by default because we believe it can help users hide noise and more easily identify the root of the regression. However, some of our more advanced users want the option to have the full picture. When we flip the toggle, we can now see the system library functions that we called into, resulting in a much larger flame graph. There's still the trail of red to our JSON method culprit, except now we can see that it calls into a number of helpers itself that are doing the actual work. Each of these helpers has a lighter shade of red, as they only contributed to a portion of the overall regression. Now, let's look at another advanced feature: flame graph inversion. In the JSON example, there was one specific stack trace where the extra time was being spent, and in that way, it was a fairly simple regression. Sometimes, however, we have a specific method called many times from many different places. This death by 1,000 paper cut scenario can contribute substantially to the overall time taken, but can be very difficult to identify in the regular flame graph view. This is where inverting comes in. It recreates the flame graph as if every stack trace sample we took was in reverse. So the top level functions of our new flame graph were previously bottom level functions. The children we see of these functions are in reality functions called into them. Instead of grouping stacks by parents, we now group them by children. An interesting example can be seen here in early startup. The next largest inverted top-level function is one that's an Objective-C runtime function initializing Objective-C class and instance methods. It has lots of children, or in reality callers, because each Objective-C method may require its own initialization at a different point in startup. Were we to convert the Wikipedia app to Swift, we probably wouldn't have this overhead, although it is possible we might introduce other sorts of overhead. Thanks for watching. Feel free to follow us on Twitter @EmergeTools for updates or to ask any questions about mobile performance.